Hello, everyone. Welcome back to some more practice on predicting. And this time we're going to be looking at single replacement reactions. Now, how do we know these are single replacement reactions? When we look at our flow chart, I see an element and a compound. So that means we're not looking at two elements. We're not looking at one compound. We're not looking at two compounds. Here I see an element and a compound, and I'm confirming this is not a hydrocarbon plus O2. So we are looking significantly at single replacement. Now, in order to predict the products, sometimes they happen, and sometimes single replacement reactions do not. So the difference here compared to combustion is that we need to decide, will this reaction actually occur or not? So one of the strategies I want to present here is an annotation technique to help you make sense of what you see. Now, we always want to note first the element that's presented by itself. What I'm going to have us do is, if it's a metal, I want us to put a box around it. And if it's a nonmetal, I want us to put a circle. Now, when you look at your periodic tables, you will notice that calcium is in column 2. So that makes it a metal. Group 2A is metals. Next, I'm going to go over to my compound and correctly box and circle my positive and negative ions. So in this case, the metal is the potassium and the iodine is the nonmetal. Now, in the lecture, it talked about the activity series. So this tool is something that can help us to identify if the reaction will occur or not. So let's get a little bit of zoom in going on here. And what happens is, as we look at this list, we're going to compare the things that have the same shape or the same type of element. So since calcium is a metal, we're going to compare it to the potassium metal. In this chart, I see that potassium is here and my calcium is here. So we see that potassium is higher on the list, which is therefore more reactive. Our bullet points at the top of the list say the higher element on the list will react or remain in the compound. The more reactive it is, the more it wants to be bonded. So since potassium is higher on the list, it's already where it wants to be. It's in the bond. That means no reaction would occur between these two substances because the more reactive metal is already bonded to the nonmetal. So we would simply write no reaction. Down here, I'm going to use my same strategy. I'm going to box the copper because it's a metal. When I look at my compound, remember, typically the metal is first. So here we have our cation silver, and that's bonded to an anion that is polyatomic. Since I have two squares, I'm going to compare those two things on my chart. I'll notice I have to scroll down a little ways to see these. In my chart, copper is one position above silver. So since it is higher, it is going to react and become part of the compound. Now I put here, use the +1 ion because copper is one that makes multiple charges. So I know that copper is a +1 and NO3 is a -1. So if I make a compound out of those two, they cancel out at CuNO3, and that one's going to be aqueous. So we would want to erase or clearly show that that is not the compound of interest. What does that leave? Well, the copper kicked the silver out of its position. So that means silver is the substance that's left, and it will show up as a solid. Didn't mean to do that. Let's move this over a little. The last thing I would need to do after predicting the products for any reaction is to check that it is balanced. When I take a look here, I have one copper on the left, one copper on the right, one silver on the left, one silver on the right, and one nitrate ion on the left, as well as one on the right. So this is also balanced. I'm just writing that down to confirm. You do not need to do that. You can just leave it as is. So please use these two examples as a model to complete the work.